All right, guys. So we have compiled a bunch of techniques for integration, and we now have lots of different classes of integrals that we are able to actually evaluate using these different techniques. What we want to do now is move into some applications, specifically arc length and surface area. And so I'm going to start here by talking about arc length and looking at really kind of motivating where the formula comes from and then putting it into practice. So let's go ahead and do that. Okay. So when we're talking about arc length, right, we're looking at something like this. Say we've got some particle and it's moving along some path, 1 plus natural log of sine t. And we want to know how far does the particle travel over the interval. And we're going to go from pi sixths to pi thirds. Now, this would be simple if it were traveling along a line. We would just have the distance formula, right? But of course, it's not, right? It's traveling along this curve. And so how do we actually find its arc length? Can we? And why is this in a calculus class? Well, you'll see. You know, one way of thinking about this is grabbing the ends, grabbing those two endpoints and just pulling it so that it's straight. But we're going to come back to this. And again, I want to motivate the arc length formula here. So let's take a look. I'm just going to draw, I guess I'll look at that same curve, sort of, that we just looked at. Maybe exaggerate it a little bit. So let's say that we're going from A to B, and we want this length. Well, what would be a good way to approximate the length? That's always a good place to start. How do I approximate the length, and can I make it better? Well, what about a partition? How about we come in here and partition that interval? And so then what we can do is create line segments on those partitions. Now, what does that do for us? How nice that we create line segments, because we can use, so let me mention what we're doing here. So we're going to partition the interval and we're going to connect the points on the curve with line segments. Well, why line segments? Well, because then we can use the distance formula. Started by saying, gosh, I sure wish instead of a curve that was a line, because then I could use the distance formula. Well, okay, how about we just create a partition and then use the distance formula a whole bunch of times? And so the length then would be approximately the sum of the lengths of the line segments. Okay. So what I've described here is the basic idea. Okay, this is the idea. Now, how do we work this out mechanically? Oops. Well, let's take a look. So I'm gonna, whoops, come back. What I'm gonna do here is look at each of these. So this first point here, right, I could call that, that's really the point A, f of A, or in a more partition-like language, A, or x naught, f of x naught. And then this second point would be x1, f of x1. And so what we could do is we could look at the, oh, I don't know, how about the ith subinterval? And then, so when I say the ith subinterval, we've got this piece of curve, right? This is the function, f of x. And then we have this line segment connecting the points. So this might be x I minus 1 f of x I minus 1. And this point up here would be f of xi, whoops, I'm sorry, would be xi f of xi. And so the length I could estimate using the distance formula. So we have xi minus xi minus 1 squared, and then the square of the differences in the y values. F of xi minus f of xi minus 1 squared, okay? But here's the deal. xi minus 1, isn't that just delta x? And so watch what happens. I get delta x squared plus, and then here's something interesting. The mean value theorem, right? There is a point somewhere in that interval where the slope of the tangent line is equal to the slope of that secant line that is our arc length, our line segment. And so using the mean value theorem, I can actually rewrite as f of, I'm going to call that xi star, meaning some special, wherever that point of tangency is, that's xi star. I know it's there. Delta x squared. And so what did I use? I used the mean value theorem. Okay. Well, now watch what happens. I've got, get rid of this here. So you've got this expression, and I'm going to play with it. I'm going to go ahead and factor some things out, see what I get. And so coming up here, I can factor out a delta x squared, and I get a 1 plus f prime of x squared, which is then the square root 1, I guess that's, sorry guys, I'm being sloppy. F prime of my xi star squared. All that times delta x. So then my arc length would be approximately the sum from I equals 1 to n, the square root, 1 plus delta x. Well, gosh, doesn't that look familiar? Right? If I wanted to know what the arc length actually is, then how many subintervals do I need? Well, infinitely many. So I would take the limit as n goes to infinity. Sum I equals 1 to n. Delta x. And gosh, doesn't that look familiar? Sure does. It's this right here. Okay? So there's the arc length formula. Where does it come from? Well, it comes from partitioning the interval, creating individual line segments, using the mean value theorem to write that length in terms of the derivative, and evaluating. Okay. So let's go back and see if we can find the arc length for this. Okay. And so before I start, might as well take the derivative, right? Because I know that's in my formula. So the derivative of natural log of sine t will be 1 over sine t times the derivative of sine t, which is cosine t. So that looks to me like cotangent t. Okay? And so now let's set this up. My arc length is going to be the integral from pi sixths to pi thirds square root of 1 plus cotangent squared t dt. Okay? Well, 1 plus cotangent squared. Does that sound familiar? It should, right? 1 plus cotangent squared. What is that also known as? That's right. It's known as cosecant squared. So we have cosecant squared, oops, not x, cosecant squared t dt pi sixths, pi thirds, cosecant t dt, and then the integral of cosecant is natural log cosecant minus cotangent pi sixths to pi thirds. And so now it's just a matter of working this out, right? So let's see, cosecant of pi thirds, 1 over sine of pi thirds. So sine of pi thirds would be root 3 over 2. So we have 2 over root 3 minus, and then cotangent is going to be, well, cosine of pi thirds is 1/2. Sine of pi thirds, we just said, is root 3 over 2. So 1/2 over root 3 over 2. It's going to be 1 over root 3. And then minus natural log cosecant, 1 over sine. Sine of pi sixths is 1/2, so that'll be 2. And then cotangent. So cosine of pi sixths is root 3 over 2. Sine is 1 over 2. So is that root 3? And gosh, I guess we could play around with this if we want. It's going to be natural log 1 over root 3 minus natural log 2 minus root 3. And if you want to combine them as a quotient, you can, but that's probably good enough for us. All right. All right. So that's arc length. And again, is it a formula that you should memorize? If you're working problems and using it, you will just memorize it. But when you look at the formula, when you see that integral from a to b square root 1 plus f prime squared, I really want you to see that whole story of its development. Taking a curve, partitioning, summing lengths of line segments, okay, and then taking a limit, okay? So you can see why that fits in a calculus class, and you can see the wonderful topics that all come into play. So it's a simple formula, but it's got some deep and rich concepts in it. I really like the way the mean value theorem comes up. And to be honest with you guys, you know, here's a big picture thought. You know, this is a calculus 2 level topic, but here's something you'll see in calc 3. You might have some curve in 3-dimensional space, and you can compute what's known as a line integral. So rather than integrating over a line segment or some interval, you're actually integrating over a curve. So picture building, it's almost like building a curtain, right? Picture a curtain all folded up, like before it's been stretched over the window, right? The bottom of that curtain forms a nice curve. Presumably the top forms the same curve. And so you're able to find that area, that curtain. That's a Calc 3 topic, but it relies heavily on our understanding and on our aptitude, ability to use comfortably this notion of arc length. So it will come back. It's very important. And again, want you to be able to digest where that formula came from, because you'll see it again, and the way that the formula is developed, specifically the use of the mean value theorem, is a very common technique in analysis and improving things later. So you will see that a common technique. Essentially, you got a difference of y values. The mean value theorem comes into play and lets you introduce the derivative. So it's useful. All right, so that is arc length. What will come next is surface area. But before that, I want you to spend some time just kind of digesting what we talked about, review this, pause it, do all that good stuff. All right, happy studies.